Hello and welcome back. In this video, I will share the solutions to all the problems from LeetCode Weekly 373 contest. The first problem is matrix similarity after cyclic shifts. You are given a zero indexed m by n integer matrix and some integer k, and you have to cyclically shift odd indexed rows to the right k times, and cyclically shift even indexed row k times. And we need to check whether the initial and the final matrices are same. Okay, this is a fairly straightforward problem. The constraints are very small, so you can use any approach as you like. So in this example, this was the initial matrix that was given to us, and this is zero based, hence this is even, odd and even. Hence, even rows are shifted to the left. Hence, this is shifted left 2 times. So initially it would be like this. So 2 1 2 1, and once again this would be shifted. This would return this row, and we can check each row independently. So the row that we have right is same as the row which was initially, and if all of those rows follow those constraints, we can return true. Let's go with the implementation. We input matrix as a two-dimensional vector and input k. We initialize OK, which is the final answer, and we also keep track of the parity of row index. Next, we go over all the rows in the matrix. We find out the size of that row, and we create the row which will be generated after performing the cyclical shift. So the logic here is that any index I in the original row would go to the position j. If it is, let's say, shifted left, then it would go at index j, or if it is shifted right, it would go at index some other index j. And let's find out what j is in both of these cases. In the left case, j is I minus k times modulo the length of the array, which would be m in this case, and in the right shifting case, j would be I plus k whole mod m. This is because after shifting one after the other, the modulo value remains the same. Hence, the last element which is present at index m minus 1, if shifted right one time, would be at index m, and m mod m would be 0. Hence, it would be placed at the first position. This is how the formula works, and using both of this formula, we can create the new row after performing cyclical shift. That is what we are doing here. I am adding a fairly large multiple m so that this value is not negative. This overall term is not negative, so that the index is valid. So for even and odd, we are applying the formula and checking whether both of these rows are same. This and is because we need to check for all the rows. This condition should be valid for all the rows. Hence, we need to check for all of them, and I'm inverting the parity or flipping the parity for even row index. And after that, we can return true or false depending on what is computed in the answer. Next question is count beautiful substrings 1. This is the easier version of that. Constraints are fairly small. So you are given a string s and a positive integer k, and vowels and consonants. These two variables are introduced, which denote the number of vowels and consonants in the string. A string is beautiful if the number of vowels is the same as the number of consonants, and this condition is also valid. The product of vowels and consonants multiplied by this, modded with this given input is 0. The multiplication of vowels and consonants is divisible by k, and we need to count the number of non-empty beautiful substrings in the given string s. Substring is a continuous sequence of characters in a string, and vowels and consonants are as defined follows. So the main observation here is to say that any string can be defined, any substring of a given string can be defined using two of its endpoints from L to R, and we need to count substrings, which is same as counting the subarrays or counting the tuples L to R, so that these two conditions are met. And since the constraints for this are fairly small, we can use the order n square approach by fixing this left index and iterating over all the right or ending index of a substring. So we first fix L, and then iterate over R and maintain these two counts for vowels and consonants, and for each of those endpoints. So this would be iterated in this manner, and at any fixed R, we'll check whether these two conditions are met. If they are met, then the answer will be incremented by 1 because it is a one valid substring that we want to find. The implementation for this is as follows. This is a utility function to check whether the character is a vowel. We check whether it is equals to one of the vowels from A, I, O, U. Next, we initialize the length and the answer we fix in the left endpoint. Then we introduce these two counters, which would be counting the number of vowels and consonants. This for a fixed L, and whenever we are jumping from one index to the other as the right endpoint, this would be updated. These two would be updated accordingly. Next, we iterate over R as the right endpoint, and the count for vowels will be increased if that character is a vowel, and the count for consonant will be increased if it is not a vowel. And the conditions, as the question mentions, are checked here. If that is met, then that means we have found one valid substring, and we can increment the answer and return. That is about this. Let's go over the next question. Next question is make lexicographically smallest array by swapping elements. You are given a zero index array of positive integers nums and a positive integer limit. In one operation, you can choose any two indices I and j and swap those numbers. Only if this condition is met. Just remember this condition, we'll come back to it later. And we need to find the lexicographically smallest array that can be formed by performing these operations. So this is the operation that we are allowed to perform over this constraint, and we need to find the lexicographically smallest array. And the definition for it is as follows. The constraints are fairly large. We cannot use the standard order n square or brute force approach. We need to think of some clever approach. So this example, we are given the array 1, 5, 3, 9, 8. In this, you can see that the limit is 2, hence 1 can be swapped with 3, only 3, and 5 can be swapped with 3, and 8 and 9 can also be swapped. So these are the possible swappings that are available to us. So one possible answer here is to swap 5 and 3 and 8 and 9, which would result in 1, 3, 5, 8 and 9. We performed these two swaps, this one and this one, and this is the best possible answer that we can arrive at for these two examples. Let's try to go over more examples and try to find out some of the observations. We saw this example. Next up, let's look at this one. We are given 1, 7, 6, 18, 2 and 1. The limit is 3. Hence, the swapping that can happen are between these elements. And one can be swapped with the last one as well. So let's also denote it using the edge. No more swapping possible for 1. 7 can only swap with 6 because limit is 3. 6 with 7, 18 with nothing. And these two can also be swapped with the original one. These are the all possible swaps that are possible that I have denoted with the red edges. Now, notice that we end up with some connected components here. So 7 and 6 lie in some single component, and this first and the last two elements lie in the other component, and 18 lies in its own component, single value. Now let's now it is obvious that you cannot swap elements from one component to the other. The swapping can only happen between the elements which are present in the same component. So let's write that down. Swapping is only possible between same components. Now let's try to figure out what is the best possible answer that we can find out for a particular component. So in this case, the 7 and 6 only had two elements. So 7, 6 had an edge, and the best way to get to a lexicographically smallest would be to keep 6 first and then a 7. Hence, this is the best answer that can be gained for this particular component. Next, we had 1, 2, and 1. The edges are as follows. Like this. Now, one thing to observe here is that it's always better to keep the smaller elements to the front, and the smallest element that can be put to the front is 1, which is already present. And since 1 can be in this place, which would make the array lexicographically more smaller, hence we will swap the second and the third elements to arrive at this, and 18 will be as it is. Now, as we saw, now these components need to be placed in their individual locations. So this 1 to 1 was changed to 1, 1, 2, hence they will be inserted at those locations. 18 was at its own initial location, and 7, 6 are like this. This is how we arrive at the final solution, which is 1, 6, 7, 18, 1, 2. Okay, let's try to figure out some observations in some generalized case. Say we have been given a sorted array, unsorted array, let's say 10, 9, 8, 7, and 6, and let's say the limit was 1. In this case, we can see that the only operations that are possible are between adjacent elements. Now, can we make this into a sorted sequence? This is already a single component. All of the elements belong to a single component. And to find out the best lexicographically smallest answer for this case, can we make it 6, 7, 8, 9, 10? We need to know if that is possible. Then it is always possible to sort the elements in a component and rearrange. So first we need to sort and then rearrange if that is the case. Let's try to figure out if it is possible. So we had 10, 9, 8, 7, and 6. The edges were as follows. Now, first of all, let's try to bring 9 to the front because it is better to keep a smaller element to the front. Hence, this would result in this case. And the edges would be like this. Right? And after this, can we again make this swapping so that 8 occurs before 9? And it is always better to keep 8 before 9 so that the answer is minimized. And it is always possible to use this edge to do that operation. Now again, the edges would be like this: 8, 9, 10, 7, 6, and an edge from 8 to 7. Notice that this operation is putting any element to the start without disturbing the prefix before it. So as we saw, initially it was 10, 9, 8, 7, 6, and this particular prefix is now reversed. You can keep performing this operation so that 7 is not to the front, then this portion is pushed back after 7, 7, 8, 9, 10, 6. So this portion is pushed back, this prefix that we are seeing in orange color, and the element that we want to bring to the front is here, and it has an edge with the last element or the element after that. And if you see clearly, this is a sorted part. Hence it is obvious to say that this entire thing can be reversed, which means we can sort the component independently, and it is always possible to bring any element at any position in a particular component. Hence component rearrangement is possible. Hence the solution boils down to finding out all the components and then sorting them individually and placing the sorted results in those locations wherever it was present. The algorithm to do that, let's try to discuss it as well, the implementation part. The way I've implemented this is as follows. So let's say we have the second example, 1, 7, 6, 18 to 1. We find out for each of those values at what location it is present. So 1 is present at, let's say I'm using 1 base indexing. So this would be 1 and 6. 2 is present at 5. Then 6 is present at 3. 7 is present at 2. And 18 is present at index 4. And notice that the component now that will be formed will be such that these values would be following the constraint as given in the question, which was this condition. Now the limit here was 3. Hence, these two can be in the same component, and these indices are belonging to the same component. Next, 2 and 6 cannot be in the same component because the difference is larger than 3. Hence, we keep them in other component. Notice that 6 and 7 can be kept in the same component because the difference is less than equal to 3, the limit, and 18 is again kept in individual one. So this is how we create components individually, and this can be done in order n time, or even order n log n, or even faster. So this is how the individual components will be found out. Next, we need to sort these values and place them in a increasing manner from left to right in the individual locations. That would be the final algorithm. Let's now move on to the implementation. This is the C++ implementation for this. Okay. If we take an input array A and the input K, we initialize the answer in which we need to store the final result. Then we store the components, the groupings as we saw in the previous diagram. So we will keep a map which denotes that E of I value is present at what locations. And this would be stored in a map, which is this. So key is the value, and these are the indices. We will store the locations for all the unique values. Then we will retrieve it in a vector so that we know in what manner we need to rearrange them. So I'm converting all the key values into a vector and sorting them individually so that the values that we saw in the previous example, let's say this one, these are all can be grouped together in a sorted manner. And this will help to check the condition that the nums of I minus, in this case it is not necessary to consider the absolute value because we are sorting it in increasing manner. Hence the constraint now changes to this. And we only need to check as long as they follow, we keep adding them in the same component, and whenever it is not following, we can end that component and process it for process answer for that component and update the answer variable. Next up, we sort. Then we will need to find out the component as we discuss here. We will start from the first index I equals to 0, and this is where the component finding happens. The component I can be extended up to I plus 1, I plus 2, all the way up to j, so that all of these elements or the values, this would be in increasing manner of a of I, a of let's say id, and these values will be lying in the same component. And after all of those are found out, so k is the limit, and we will retrieve all the values that are present in that locations, the positions and the respective values. Position is the value which is present in the second part of the pair in which values are stored, and the first is the actual value, the array value, and which will be populated in these two values. Then we will need to individually sort them and place them in the final answer at corresponding positions. And once this is done, that means we have processed one component. So we started with I equals to 0, then I equals to 1. Then we notice that these two cannot be matched because the limit is 3 and the difference here is 4. Hence, then after we processed this component, and after that is done, we will start the iteration for finding out the next component from index j, which was the previous index's next value. This is how we will compute all the components and update the answer in the final sequence and return it from this function. That is it about this. Let's move on to the next question, final one. This is the slightly harder version of problem 2. Let's try to understand this. You are given a string s and integer k, and the vowels and consonants are defined the same as we saw in the previous discussion. Only the thing that has changed here is the constraints on the length and key. Okay, let's try to make some of the observations for each of these two cases. Let's try to understand them. So one thing to note here is that any substring of a string s, say s1, s2, all the way up to sn, is defined using two endpoints l and r, and this substring must follow some of the properties that is mentioned in the question. The first being the number of vowels is equal to the number of consonants. Notice that there are only two types of characters in this given string. Hence, we can map them to plus and minus 1. It is helpful because we can represent the vowels as plus 1 and consonants as minus 1. And let's see how that is going to help us. If we represent the vowels, let's say A, Z, X, E, I, O, U, using plus 1 for vowels and minus 1 for consonants, that would change the first condition so that the number of vowels is equal to the number of consonants, means that any substring, so this substring, which is defined by the endpoints l and r, will have sum equals to 0. That, which is the same as saying that the number of vowels is same as consonants. If the number of pluses and the number of minuses are equal, that means it has the same number of vowels and consonants. That is the first observation. And from this, we can also create an auxiliary dynamic array, which is the prefix sums, which denotes the sum of the values in the string. So let's say the initializations of plus and minus 1 is defined by the array A. Then the first sum of the first elements is given the prefix of I, which is the sum of the values from 1 to I. And this can be computed in order and time. So let's keep this value in mind whenever we are going to represent these conditions as given in the question. Whenever vowels is same as consonants, that means the sum of that particular subarray is 0. Now sum of any subarray in this given array from L to R would be defined by prefix of R minus prefix of L minus 1. Right? And we want this to be 0 since this condition is what we want to follow. If that is 0, that means the prefix sums of the endpoints of the array of this subarray are same. So if you have a prefix This is the prefix array of the converted input, and the prefix array looks as follows: 6, 6, 6, 6. Then that means that this subarray is follows the first condition, even. So this is L minus 1 and this is R, hence, except that this is the subarray that we are looking at, and this follows the condition 1. Now we have figured out some calculation for first part. Let's move on to the second one. Now the thing to notice here is that once we know what all pairs follow this first condition, so we know that any pair wherever prefix of J is, let's say, prefix of R is same as prefix of L, that means that these two values are same for L and R, and this subarray just after L is not considered because it is excluded from the sum and it is counted. It only determines the sum for the prefix from 1 to R. This is the subarray for which vowels is same as consonants. Now we can group all the prefixes for which this condition is followed. So if the prefix array has the following values, say 6, 6, 7, 8, 9, 6, 8, 7 at the positions 1, 2, 4, 6, 7, and 8, we can group them as follows. We can say that 6 is present at locations 1, 2, and 6. Then 7 is present at 3 and 8. 8 is present at 4 and 7. 9 is present at 5. Now the interesting property to note here is that if you take any of this grouping, then any pair taken as L and R in this grouping follows the conditions for number of vowels is equal to number of consonants, because we have grouped them based on the condition as we derived earlier. Now you need to individually solve the answer for each of this grouping, and that grouping, now we have completed the first constraint, right? This is what we have followed until now, and now in that grouping, that means for a particular subarray for which the first condition is valid, we need to check how many of those pairs follow the second condition, so that we want both the conditions simultaneously to be followed. Now let's try to understand how we can individually find out this. The second condition mentions that we want the number of vowels times the number of consonants mod equals to 0. Now if we have some grouping, the value is, let's say, x, and the locations in which it is present is, let's say, x1, x2, x3, all the way up to xk. Now as we derived earlier, any two values taken as L and R in this would mean that that subarray has number of vowels equals to the number of consonants. And the second condition to follow here is vowels times consonants mod t is 0. Now this subarray has the number of, this condition is satisfied. Let's try to figure out how this condition can be altered to help us. Since vowels is equal to consonant, this can be written as v square. Now v is the number of vowels and number of consonants is same, and this can be found out by this formula. Since both of them are same, and let's say the length of the subarray was 10, both of them are same, hence they must be 5 each. Hence the number of vowels would be length divided by 2 of that particular subarray. Now we can substitute those values here, and this is what we want to find out. But here, since there is a square, it is not feasible to just fix one of this variable and count the number of L's, because if you expand this, this would give us r square plus L square minus 2rl whole divided by 2 mod k equals to 0. And again, the terms, only the terms where L is present is not easily separable, hence we need to convert this into a simpler approach. So what we can do is we want this and this to have the same modulo. For that, we can take the square root of this term. So let's say this was LHS, this was RHS. After taking the square root, we arrive at this equals to, the mod value should be same, which would be this equals to k raised to 1 by 2. After separating 2 as well, we get 2 times square root of k. Now if we want to know that this modded with this entire term is equals to 0, that means we can iterate over one of the variables and count the other variables count. But to do that, this is not necessarily an integral part, so we need to understand first how we are going to check whether the numerator is divisible by a denominator. This fraction is divisible, that means n is divisible by d only when the condition is as follows. So let's say the prime factorization of n is as follows. So p raised to, let's say, a0, a1, a2, and so on. And the denominator consists of b0, b1, b2, and so on. Now the condition of divisibility is possible only when a0 is greater than equals to b0, as well as a1 is greater than equals to b1, a2 is greater than equals to b2, and so on, for all the terms that are present in the exponents of the prime factorization of both numbers. And notice that we have this term as the numerator and this term as the denominator. So numerator is r minus l and denominator is 2 times k raised to 1 by 2. If you put the prime factorization of k here as p0 raised to b0, p0 raised to b1, all the way up to pk raised to pk, and this is taken to the power 1 by 2, we would have some of the equations, these equations changed as follows. Here we would have a0 to be greater than equals to, now this exponent here, initially it was b0 if it was a standard case, but here since we have power and a term in the denominator, this would be changed to b0 by 2, and a1 would be b1 by 2, a2 would be b2 by 2, and so on. Notice that there is also 2 here, that means if one of the prime factorization here it contains 2, so if, sorry, this should be p1, if some pi is 2, there is even number in a 2 in the prime factorization of k, that means that particular power would be added for this 2 as well. So if p0 is 2, in that case a0 condition would be like this, right? So this is what we need to follow to convert this into a new value for which we need to take the mod. So we want r minus l modded with the new value for k that we are going to find out to be equal to 0, and this new k would be the minimum value for ai, for which we need to know that the numerator divides the denominator, and denominator is the new k. And if this could be a fraction, then we need to take the ceiling value for each of them, because if the condition says that a0 is greater than or equals to 3.5, then that means it must be greater than or equals to 4, because this belongs to a integer. Hence we will find out the new k for which the numerator is r minus l, which is separate from the square value that we saw earlier. The new k would be p0 raised to a0, not a0 but p0 by 2, the ceiling value, p1 raised to p1 by 2, p2 raised to p2 by 2, and so on, with the only condition that this could be also p0 by 2 plus 1 if there is a 2 in the prime factorization of k, so that this 2 and a 2 in its own prime factorization is also considered. So this would be considered if there is no 2 in the prime factorization, or the first one would be considered, else the second one would be considered. Now you know the new k, for which you only need to check the condition, which would be as follows. So now we need to check whether r minus l modded with the new k is 0. Hence we can fix one of the endpoint and count the other ones that are valid. And to do that, you only need to count the number of occurrences of a particular prefix in the array that we want to find out. So this is the explanation to keep k new as this expression, which was the least possible value for a0, a1, and a2, and so on, is as follows. So we want this term to be divisible by this numerator to divisible by denominator, and this denominator had a term which was like this, and it had some fractional expression in the exponents. So if it was something like 2 raised to 3.5, 3 raised to 6, 7 raised to 1.5, and so on, and the numerator had 2 raised to, let's say, 6, then we want the denominator to have the smallest value which is greater than or equals to this power. So we want ai to be greater than or equals to bi, right? So that that particular prime factor is divisible by the denominator. Hence the smallest value that can be possible is kept as the power whenever we are converting this expression into the new key as denominator. That is it about this. We find out the new key, and the expression turns out to be, to find out, since we perform the grouping for any particular group, we have the indices i1, i2, all the way up to, let's say, ik. In this, we need to count the number of pairs such that this condition is followed. To do that, we can use map to count the valid pairs. Let's look at the implementation to understand it better. Okay, we have two utility functions to find out whether the character is a vowel or not, and to find out the value for the exponent of any value. And we have been given string s and key as input. We find out the prefix I, which is the, first of all, the substitution plus minus 1. Vowel is substituted as plus 1 and consonant as minus 1. After that is done, we find out the prefix sums of array, which is the, so this was the initialization to the converting string into array, and we then convert this into a prefix array using this formula. Now to find out the new key, we find out the prime factorization of k. So k is, let's say, the product of pi raised to ei, and from that we will find out new k. So if any particular prime is divisible by k, we find out what exponent is that in its prime factorization by simultaneously dividing it until that particular prime factor disappears from its prime factorization, and then the exponent in k news prime factorization, let's say pi raised to xi, is computed as follows. So we know that xi is the ceiling value of ei by 2, and it is plus 1 only when the prime factor that we are consider is 2. This is what we are doing here. We find out the exponent in the prime factorization of the new key value, and that particular part is multiplied. So since this is a product of individual prime factorization and their exponents, so we are multiplying the contribution of particular prime here. After that, we change the k to the value that we computed and create the groupings so that we maintain a pair instead of, to follow both of the conditions I mentioned in the question. We want the vowels to also be same and these conditions should also be met. And this is done by the following implementation. We know that the first condition is met when sum is 0. That means the prefix values are same. Hence that is what we are going to store in the first key of the hash map. The prefix values for particular endpoint fixed r. So we are fixing r and we need to count how many valid L's are there for fixed r. So in a particular grouping, if we fixed this value for a group, next up we need to know that r minus L mod k, which is the new k, is 0. And to do that we only need to know, so this equation transforms to saying that the indices have the same mod r key value. So that means we only need to know what is the count of r mod k. So we are iterating over r at a particular index, and for all the candidates of L which is less than r, behind it, which are valid ones, will follow this condition. So we need to know how many such possible L's are there which are present behind r, and that particular count will be the number of subarrays that are possible ending at index r. And again, the contribution for this particular index that we have been processing would be added in the answer or the counter by saying that there is one index for which it has a prefix of I as the first key, and the second condition constraint as the index mod key. And this is the case where we need to choose the entire prefix. Suppose we are at index 0, there is nothing behind it. That means that prefix, all the prefix, complete prefix should also be considered in the answer, so that we also have the answer for the complete prefix initialized with 0, 0 as 1. And this would compute the answer for all the substrings, and the final answer will be the count of various substrings that are asked in the question. That is it about this video. If you found this useful, or if you have any doubts or suggestions, do let me know in the comments. Thank you.